Now that we have our sort of algebra review, algebra basics as far as polynomials and types of factors out of the way, let's now start going through the actual process of doing a partial fraction decomposition. And again, we're going to break it up over several videos based on the type of factorization that occurs. So the first type that we're going to look at, right? So remember, our goal is to be able to integrate functions of this form, these rational functions. And what we're going to look at now is case one. And case one assumes that we have a proper rational function where the denominator has only simple linear factors, right? So here are the assumptions. One, f of x is a proper rational function, right? And we now know what that means. And then two, the q of x consists of only simple linear factors. All right. So that means when we factor the denominator, we're only going to get simple linear factors. So nothing will be repeated and nothing will be irreducible quadratics. Those will be handled in separate cases, right? Okay. So here is sort of the general rule for this. So if q of x has the following factorization, right? And notice it's not telling us how to factor. That's something we're going to have to figure out, right? So we're going to have to rely on our algebra skills for that. But it's saying that if the denominator has this factorization, so like a1x plus b1, so there's one linear factor, a2x plus b2, there is another linear factor, and let's say it goes up to n of these things, a sub n x plus b sub n, where all the a's and all the b's are real constants. So I'll just say that the a sub I, the b sub I are all real. So if that's the case, then it is possible, right, to decompose this rational, this single fraction into the following form. So if q of x has the following factorization, then f of x, which is equal to p of x over q of x, can be decomposed in this way. So may be decomposed as, and this is what it looks like. We can have a constant over the first simple linear factor, the a1 x1 plus b1. And notice I'm using this constant. I'm using an uppercase A, right? So it's not this A, it's a different number. And then plus a2 over the second factor that I have listed, a2x plus b2, and so on up until we get to this last factor. And then again, you'll have another constant on top, right? And the thing is, where the big A1, the big A2, the big AN, all of these constants are to be determined. And that's the real crux of this process. So where A1, A2, dot, 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 A sub n are constants to be determined. And I will show you two ways that you can actually determine these constants once we start looking at examples, right? But basically, so for this case, if when we factor our denominator, if we only get simple linear factors of this form, then it means that this single fraction can be decomposed in this manner, right? And then we'll then determine how to figure out these constants. All right, so let's see an example. And right, so example. So suppose we have to evaluate the antiderivative of x plus 31 over x squared minus x minus 20 with respect to x, right? Again, when we kind of think of all the techniques that we've looked at up to this point, it doesn't, just kind of at a quick glance, it doesn't look like any other technique will really work. You know, if we try to use the u with our denominator, that doesn't really work, right? Because we don't have the 31 here. And no other technique really appears to work. So we're going to try our partial fraction decomposition. So the next few steps that we're going to do, it will be a lot of algebra, right? In fact, I would say probably 90 or 95% of these questions is algebraic, and just, you know, a much smaller proportion is actual calculus. So let's take the x plus 31 over x squared minus x minus 20. We can see that it's proper because the degree of the numerator is 1, but the degree of the denominator is 2. So once your denominator has a greater degree than the top, then we know it's proper. Let's see if we can factor the denominator. So the x plus 31 all over, and yeah, so this one factors nicely. It's x plus 4 times x minus 5, and there are our two simple linear factors. And what this rule says for partial fraction decomposition, it says there is a way that I can take this single fraction and write it as the sum or difference of two fractions that look like this: a constant over x minus 4, x plus 4, and then plus another constant over x minus 5. Right? So the question is, so basically, in fact, let me make a stronger statement here. These are not just equations, right? What we're saying is clearly these are identical, right? So no matter what value of x I plug in here or I plug in here, these two fractions will be identical. And what partial fraction decomposition is saying, well, there's a third identical form of this, and it looks like this, right? So these three lines, it's stronger than an equation. You read these as saying is identical to. Right? And there's a big difference between an equation versus an identity. An equation is a mathematical statement that is true for some values, possibly some values of your variable. An identity is a statement that's true for all values of your variables. So what we want to figure out, we want to figure out what the constant A1 is and what the constant A2 is, so that these two fractions are identical regardless of what values of x I plug in. So how do we figure out A1 and A2? Well, I'll show you the two methods now. So let's focus on this form right here. Right? Now, if I wanted, for instance, to clear the fractions, right? So if I wanted to clear the fractions, what I could do, I could multiply both sides by the x plus 4 and the x minus 5. So basically take this product here, multiply the left, and multiply each of the fractions on the right. So it looks like this. So I'll just refer to that as like clearing fractions. Right? In fact, you do this regardless of which of the methods that I'm about to show you that you're using. So if I multiply both sides by this denominator, I'm going to be left with x plus 31 on this side, and then I'll have my identity symbol there, and then I would have x plus 4 times x minus 5 times a1 over x plus 4, and then plus the x plus 4 times x minus 5 times a2 over x minus 5, right? So basically just take the denominator that was on the left and multiply both terms on the right. Now you can see why the fractions get cleared, because they have a common factor there, common factor there. So again, all we're doing is just we're rewriting this identity, right? We're saying that these two things are identical. I'm just writing it in a more convenient form. So I have x plus 31 is identical to, so now let me put the constant in front and say whatever a1 is times x minus 5 plus whatever a2 is times x plus 4, right? Now, here is the first method. The first method is where we can choose, since this is an identity, right? And remember, an identity is true regardless of the variable, the value of x, right? What I can do, I can choose appropriate values of x that will simplify the right-hand side so that I can solve for each of my constants, right? So because this is an identity, let's write that. So because this is an identity, we may choose, and I'll say, put it in quotes, like convenient or appropriate values of x. So convenient values of x, right? That will simplify the left-hand side or right-hand side. So that simplify the right-hand side, making it possible to solve for a1 and a2. So making it possible to solve for a1 and a2, right? So when I look at this, I say, well, you know what? If I let x equals 5, then it will cancel out this term altogether, because I would have 5 minus 5 there. And then I would have an equation or an identity that only has one unknown, right? See, right now there are two unknowns. But because it's an identity and I have the ability to plug in any values of x I want, because it's not going to change the truth value of the statement, right? I can pick any values of x that I identify as being convenient. Convenient in the sense that they will eliminate one of the terms, right? Or maybe more of the terms. What if we had more terms over here, right? So the first thing I'm going to do is I'm going to let x equals 5. When I do that, the left-hand side becomes 36. In fact, let me go ahead and just write that in. So 5 plus 31, that has to be identical to a1 times 5 minus 5 plus a2 times 5 plus 4, right? So this simplifies to 36. This simplifies to 0. And then this simplifies to 9a2. So therefore, A2 has to be equal to 4, right? So A2 must be equal to 4, right? So by making this choice, I eliminated this term and it allowed me to solve for A2. So then I repeat this process. Why not pick a value of x that will eliminate this term, but then allows me to solve for A1? So looking at this, if I let x equals -4, then this factor is 0, this whole term goes to 0, and then I'll be able to get my A1, right? So let's make that as a choice. So if we let x be equal to -4, and again, why can we do this? Because it's an identity, right? It's not like just some equation that's true for certain values of x. This is true for all values of x. So if we plug -4 in, again, I'll just plug it in each spot, and then we can simplify. So we have A1 times, and then -4 minus 5, and then plus A2 times -4 plus 4. So that eliminates that term. We have 0. What do we have here? This is 27. And then that's identical. This is -9A1. And there's our 0. So we've eliminated that term. And then now I can solve for A1. That tells me that A1 has to be -3. Just dividing the 27 by -9, right? So there we go. We have our -3. So with this, I can complete my partial fraction decomposition, right? Remember up here, I had that, in fact, I can go back up here now and write that completed form. So I can say that this is now identical. My A1 was -3. And then my A2, we got that to be 4, right? So through this algebraic process, we're able to take this single rational function that happens to be proper, and we were able to write it as the sum of two, I would say, simpler, but they're still rational, they're still proper functions. So instead of one big fraction, now we have a sum to integrate. But a sum is much easier to integrate than a product or something complicated like this, because we can integrate it term by term. All right, so now let's finish the problem, right? So again, I always like to go back to the original. So we have the x plus 31 over the x squared, what was it, minus x minus 20 dx. We decomposed this, and we got it to the form -3 over x plus 4 dx plus the integral of 4 over x minus 5 dx. And then we can factor out our constants. So we have -3 outside the first integral. And then now factor out the 4. And then we have 1 over x minus 5 dx. Now, what will happen whenever you have simple linear factors? These antiderivatives will always be ln. Always. Because you're not going to have anything raised to any power, right? So it's always going to be the ln. And in this case, it's going to be -3 times the natural log of x plus 4, and then plus 4 times the natural log of x minus 5. And what we're able to utilize here is that basic result from Calc 1. Right? Now, the other thing to keep in mind is sometimes if the coefficient of the linear factor, if the leading coefficient is not 1, you might have to divide by a constant, like doing the reverse of the chain rule. And we'll see an example of this. All right. All right, so let's do another example of this, and in that example, I'll show you an alternative way of figuring out the constants. All right, so let's try another example. And in this case, let's do a definite integral. All right, so here is our definite integral. So 7x squared plus 63x plus 52 all over 3x cubed plus x squared minus 48x minus 16 dx, right? So this is our integral. And we can see it's rational, right? Definitely a rational function. We can see our two polynomials, and we check our degrees, and we see that it's proper. Now, we won't know that it is which case it is, if it's case 1 or some other case, until we actually factor the denominator, right? That's the key here. We have to see what the factorization of the denominator is to see if we can do it. So let's actually do that factorization separately. So if I do 3x cubed plus x squared minus 48x minus 16. Well, one of the things that you try when you have an even number of terms, so we have 4 terms in this polynomial, right? It's a third degree polynomial. We try to factor by grouping. So what I'm going to do is I'm going to group the first pair. So we're going to group the 3x cubed plus x squared, and then plus, and then I'm going to put the negative inside the parentheses, group the last pair. So the minus 48x minus 16. And then you look to take out a greatest common factor. Well, out of the first pair, I can factor out an x squared. And then that leaves me with 3x plus 1. And then out of the second pair, I can factor out a negative 16. And then that leaves, again, a 3x plus 1. And whenever you see the same factor in parentheses show up, then you know that, okay, yep, this method works. Sometimes it doesn't work, and you have to try something else. So we can now factor out 3x plus 1, and then that leaves me a factor of x squared minus 16. So right now it looks like I definitely see a simple linear factor here, and it looks it's a quadratic, but if you notice, this is a difference of 2 squares. So this can be factored even further. Now let me just factor it on this line. So then here's the full factorization of the denominator. It's the quantity 3x plus 1 times x minus 4 times x plus 4, right? And there we go. So all simple linear factors. All right. So what does this mean? Well, it means my rational function, the 7x squared plus 63x plus 52 all over the, let me now write the factored denominator, 3x plus 1 times x minus 4 times x plus 4. That is now based on what the partial fraction decomposition rule states, that this single fraction can be written as the sum of 3 smaller fractions. The first one, now I don't have to use the A1, I'm just going to use A and then B and C, right? So you don't have to use the A's with the subscripts. Once you know how many constants you're going to have, you can just use the letters A, B, C, D, etc. So I'm going to put A over the first factor, and then plus B over the middle factor, and then plus c over the third factor, right? And this decomposition is always possible based on what we know about polynomials and now these rational functions, right? So let's clear the fractions, and what we're going to do is take this denominator and multiply both sides. Well, when I do that, I am going to have 7x squared plus 63x plus 52 that's left on the left-hand side. Now, if I take this denominator and multiply the first fraction, the 3x plus 1 will cancel out, and I'm going to be left with a times x minus 4 times x plus 4. And then also, if I take this same denominator, multiply the middle fraction, then the x minus 4 will be canceled out, and then I'll be left with b times 3x plus 1 times x plus 4. And then finally, if I take again the same denominator and multiply now the third fraction here, the x plus 4 will cancel out, and I'm left with my constant times 3x plus 1 times the quantity x minus 4. All right? So now in this case, we could use the same procedure that I did in the first example and pick different values of x to cancel things out, and it would work, but I want to show you an alternative way of doing it. And on the surface, it's going to seem a little longer than just plugging values in, but this method is guaranteed to always work, and it works well, in fact very well, in some of the other cases that we have to look at. So what I'm going to do is FOIL out each of these products. So the first one, that's a difference of 2 squares, so I'll have the x squared minus 16. And then over here, I will have the, let's see, so we'll have b, and we'll have 3x squared, and then I will have a 12x, and then plus a 1x, so that's 13x, and then my constant is 4. And then plus c times, again expand this, I will have 3x squared, and then I'll have a minus 12x plus 1, so that's a minus 11x, and then I'll have 1 times negative 4, so that's minus 4. Now let's collect the like terms on this side. Right, so I'll just keep bringing down my quadratic on the left, and on the right, let's look for the like terms. Well, as far as the x squared goes, I'll have ax squared plus 3bx squared plus 3cx squared, right? And then let's see, as far as the x goes, so I don't have any x here, but I have a 13bx, so plus 13bx. And then here I have a minus 11c times x, so minus 11cx. And then let's write down the constant. So now I have a minus 16a, and then a plus 4b, and then a minus 4c. Right? So what we're actually doing is we're trying to write the expression on the right hand side of this identity so that it looks like a standard quadratic. But the thing is, there are some numbers that we don't know, right? But I can still write it in that form. So let's say out of the first 3 terms, I can factor out an x squared. So it looks like a plus 3b plus 3c, that quantity times x squared. And then now if I factor out an x over here, I will have 13b minus 11c times x. And then here would be my constant, so I'm going to write it as plus negative 16a plus 4b minus 4c. Right? Well, how does this help? Well, the thing is, we're saying that these two quadratics are identical. That's what this statement is saying, that this quadratic on the left is identical to this quadratic on the right. That means whatever is multiplying the x squared on this side has to be equal to whatever is multiplying x squared on this side. Whatever is multiplying the x on this side has to be equal to whatever is multiplying the x on this side. And then finally, whatever the constant is on this side, that's equal to the constant on this side. So what that gives us now is a system of linear equations. So what I have is this. I have that a plus 3b plus 3c is equal to 7. I have that 13b minus 11c is equal to 63. And then I have negative 16a plus 4b minus 4c is equal to 52. Right? This process here is called comparing coefficients. And it's a really powerful technique that works well for polynomials. Because the only way two polynomials can be equivalent or identical is if they have the same degree and all the coefficients have to be equal to each other. So whatever the coefficient is of x squared on this side has to be the same as the coefficient of x squared on this side, and that has to be true for all coefficients in the polynomial. So then we have some algebra to do. We have to figure out how to solve for a, b, and c. Well, I am going to assume that you have been exposed to solving linear systems. I'm just going to show you one way. What I'm going to do is solve for a from the first equation, and I'm going to eliminate it in the third equation, and then use the second and third equations to solve for b and c, and then plug my answer back in to get a. Right? So let's do that. So we got negative 3b minus 3c plus 7, right? So take this and plug it right there, right? So I'm going to essentially reduce the system to two equations, two unknowns. So the second equation won't change right now, so I have 13b minus 11c is equal to 63. And then I'll have negative 16 times what I have here for a. So negative 3b minus 3c plus 7, and then plus 4b, and then minus 4c, and then that's equal to 52. Distribute the negative 16. What do we have? So that's a positive 48b, and then a positive 48c, and then this is a negative, what's that? 112, and then plus 4b, and then minus 4c, and that's equal to 52. Let's collect the like terms and then move the constant over. So we have 48b plus 4b, so that's 52b. And then we have minus 44c. And then add 112 to both sides, so that gives us 164. So we have this equation now, and then this equation now, right? Let's see if we can solve this. So what could we do? All right, so now we have our equations that involve only b and c, and this, let me make one correction here because this should be a positive 44c because we have 48c minus 4c, so that should be a plus. Okay. Okay, so let me write these two together and see if we can figure this out. So if we have 13b minus 11c is equal to 63, and then down here if I have 52b plus 44c is equal to 164. Well, again, I could do something similar, or I could use another procedure, and if I multiply the top equation by 4, so let's say I multiply the top equation by 4, right? And if I add, that will eliminate the c's, right? So if I multiply the top equation by 4, I end up getting, let's see, so 52b minus 44c is equal to 252, and then my second equation stays the same. 52b plus 44c is equal to 164. So if I add these, I have 104b. The c's cancel out. And what do I have here? So I have, let's see, so that's 614. And then dividing both sides by b, I get to get b, I divide both sides by 104, and b is equal to 4. So b is equal to 4. Then I can plug it back in anywhere to find my c. So let's say I go back to this equation. So when b is equal to 4, plug 4 in there, I have 208. So I have 208 plus 44c is equal to 164. And then 164 minus 208, so that is a negative 44. So I have 44c is equal to negative 44. So that means c is negative 1. All right. And then now that I know b and c, I can go back to this equation to figure out a. Right. So when b is equal to 4 and c is equal to negative 1, then a is equal to negative 3 times b, that's negative 12, and then minus 3 times negative 1, so that becomes plus 3, and then plus 7. So then my a comes out to be negative 2. All right. So again, let's highlight. So the big things here now is that we've figured out a, b, and c. Now you can see there was a bit of algebra that we had to do, right? So what does this mean? So it means our original, so let's write down our integral. This is what we had to do, is the integral from 0 to 2 of 7x squared plus 63x plus 52 all over that 3x cubed plus x squared minus 48x minus 16 dx. Well, that's the same as integrating. What do we have? So we have the negative 2 over the 3x plus 1, and then minus 1, well, let's see, plus negative 1 over x plus 4, and then plus 4 over x minus 4, right? And that's from 0 to 2. All right. So now we can integrate term by term. And if we think of these as three separate definite integrals, using our properties of definite integrals, we can take out the negative 2, integrate from 0 to 2, 1 over 3x plus 1 dx, take out the negative 1, and then integrate the 1 over x plus 4 from 0 to 2 with respect to x, take out the 4, and integrate from 0 to 2 the 1 over x minus 4 dx. And each of these will be the ln. But the first one we have to be careful of because we have this extra constant, this extra 3. So it is going to be negative 2 times 1/3 because we're going to have to divide by that 3, and then the ln of 3x plus 1, and then minus the ln of x plus 4, x plus 4, and then plus 4 times the natural log of x minus 4, and then this has to be evaluated at 0 and at 2. Alright, so let's see what happens. At the upper, actually what I need to do here is I have to put absolute values for these ln's. So let's fix this. So these are absolute values. That way we don't end up taking the natural log of something negative. So absolute value of 3x plus 1, absolute value of x plus 4, absolute value of x minus 4. Right. All right, so let's see. So when at the upper limit, we have negative 2/3 times the ln of 7, and then minus the ln of 6, and here I'm taking the absolute value as well. And then here, now here we would have the ln of the absolute value of negative 2, but that absolute value changes it to positive 2, so plus the ln of 2. So that's at the upper limit, and then at the lower limit, when we plug 0 in, what do we get? Again, negative 2/3, ln of 1, which is 0, so that's 0, and then minus the ln of 4, and then plus 4 times the ln of the absolute value of negative 4, and that absolute value makes it a positive 4. All right. And I mean, there's not much we can do with this, so I'm just going to write this down. So it's negative 2/3 ln of 7 minus the ln of 6 plus 4 natural log of 2. This term here is 0. Then distribute the negative sign, so I have plus the ln of 4. And then what do we have here? So minus 4 ln of 4. So minus 4 ln of 4. Right? I mean, and that's the now. So we could apply properties of logarithms to combine this into one log. I mean, if you want to see what that's like, this is what it looks like. So you'd have the ln of 7 to the negative 2/3 power, and then you'll have plus the ln of 6 to the negative 1 power, bringing up that negative 1. Then you'll have plus the ln of 2 to the 4th power, plus the ln of 4, plus the ln of 4 to the negative 4 power. And then since we're adding all these logarithms, it's the log of the product of all of these numbers. So 7 to the negative 2/3 times 6 to the negative 1 times 2 to the 4th times 4 times 4 to the negative 4. And if you didn't want those negative exponents, you could do this. So it's the ln of, now at the top, we have 2 to the 4th, which is 16, times another 4, so that's 64. And then all over, if I take the reciprocal of these, I'll have 7 to the 2/3, and then times 6, and then I would have 4 to the 4th power down there. So that's how you could write it as a single logarithm. And this could be reduced further, and we could go on and on and on. But I think this is a good place to stop. So this was definitely a long question because of the amount of algebra that's involved, right? The actual calculus really only occurred at this step, right? So right here, going from this to this is the only step where we actually used calculus in this entire solution. So if we scroll back up to look at all the stuff that we did, that's a lot of work, right? But that's what we have to do in our partial fraction decomposition. So next up, we will look at the case where we have repeated linear factors, and we'll see how that one works. Right? See you then.